Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we'll be looking at ways of writing material balances for systems with multiple reactions. And our goal is that you will then be able to solve material balance problems, whether you are doing this with mass balances or mole balances. So we're going to look at both. We want to do this for the example here, the catalyzed combustion of ammonia. There are two reactions, 4 ammonia gas molecules plus 5 oxygen gas molecules make 4 NO and 6 water, all in the gas phase. But 2 NOs react with the O2 to make 2 NO2s. And so we're going to start with a closed vessel that initially contains 5 moles of ammonia and 10 moles of oxygen. And we want to use extensive reaction to write a mass and a mole balance on each species and on the total material. Now I'm going to start with the mole balance because that's the easier one. So we know that we have 5 moles of ammonia and 10 moles of oxygen and nothing else. So let's write those down. Now we also need to consider what other components we have. And we know that we will be creating NO and H2O, and we will be creating NO2. But initially we have none of these. When we leave, that's going to depend on how much reaction has occurred. And in terms of moles, we can do this using the stoichiometric coefficients. So for NH3, there are 4 NH3 in the first reaction, but it's on the reactant side, so therefore it's 5, we started with 5, minus 4x1 will be what leaves. Oxygen, we started with 10. The stoichiometric coefficient is 5. It's a reactant, so 10 minus 5x1. So the extent of reaction for the first reaction, it's going to use up 4 x1s and 5 O2s, 4 ammonias and 5 oxygens. Did not say that very clearly, sorry. But I also know that I'm going to create. So I start with 0 and I create 4 nitrous or NOs and 6 H2Os. But I have reaction 2 also occurring. So in reaction 2, I have NO being consumed, so minus a stoichiometric coefficient of 2, X for reaction 2, oxygen with a stoichiometric coefficient of 1, so minus X2, and NO2 is being formed, so 0 plus 2 extent of reaction of species 2. So this is the number of moles of NH3. This is the number of moles of O2, the number of moles of NO, the number of moles of H2O, and the number of moles of NO2. What about a total material balance? Well, I just add those up. So if I add these up, I started with 15. I have, for x1s, I have minus 4 minus 5 plus 4 plus 6 plus 2. So, no, excuse me, that's not plus 2, plus 4 plus 6. So I end up with plus x1. So I've added a mole based on the extent of reaction in reaction 1. And for reaction 2, I have minus 2 more, plus 2, so minus x2, and this is N total. So if this is N is 15 plus x1 minus x2. I could use that if I wanted to. I could tell you what the mole fraction at the exit would be. So for instance, for NH3, it's the number of moles of NH3 divided by the total number of moles. Right? And I could do that for any of my species. I have two unknowns here, x1 and x2, and so I could use that, okay, in solving a problem once I had, enough information to know where it's going to stop. Now, what about the mass balance? To write a mass balance, I need to know the molecular weights of these species. So the molecular weight, well, for NH3, we can look these up. And so we have this information. I could therefore write the mass of NH3 is going to simply be 5 minus 4x1 times 17.031. The mass of O2 is 10 minus 5x1 minus x2 times 31.999, etc. And I could continue that pattern all the way down. If I wish to add this up and find the total m, so I could get mole or mass fractions, well, the expression is going to be a little bit ugly. It is 405.145, that's the initial mass, plus x1 times, and when I write all these out, I have that for x1 plus x2 times negative 31.99 minus 60.012 plus 92.012. And what I find is that m is 405.145. You can play with the numbers and verify that. But the mass doesn't change. So that aspect of the material balance is easier with mass because mass in equals mass out. However, having to mess with those equations with these molecular weights is an extra complication and makes our numbers a little bit uglier. But you should now be prepared to work with either mass balance or mole balance with multiple chemical reactions. Thank you very much for your time.